My name is Hunter Manning, and this is Lab 1 of Physics 2211. The following is a brief glimpse at what I'll be discussing in this video. You may return to this section if you have any questions. The purpose of this lab experiment is to analyze and apply Newton's fundamental laws of motion to real-world scenarios. This experiment focuses on Newton's second law of motion, the momentum principle. This principle is tested by comparing two position time graphs, with one comprised of experimental data and the other comprised of data produced by a computational model. Briefly touching on the results of this experiment, the experiment was relatively unsuccessful as a change in velocity was recorded, indicating a non-zero net force and thus a non-constant velocity. In this experiment, the system being studied is the baseball itself, and the surroundings include the floor and the air. If there is no net force acting on the system, then there will be no change in momentum, and the velocity will remain constant. This idea is seen by the velocity update formula on the next slide, where when net force is zero, the equation equates the final velocity to the initial velocity, indicating a constant velocity. This is also supported by Newton's first law of motion, which states that objects in motion will remain in motion in a straight line unless acted on by unbalanced forces. As you can see, the velocity update formula states that the final velocity is equal to the initial velocity plus the net force divided by mass times delta t. The momentum update formula states that the final momentum is equal to the initial momentum plus the net force times the change in time. An important concept to remember is that momentum, velocity, and net force are vector quantities, meaning they have both direction and magnitude. I will now cover my experimental procedure. First, I recorded the baseball rolling in the positive x direction. I then imported the recorded video into the tracker software and recorded the baseball's position at each frame. I then created a computational model with the provided GlowScript template using unique data from my experiment. I used Excel to create a position versus time graph for both the tracker and computational models. Finally, I compared the two graphs. Moving on to the motion analysis, I pushed the baseball from left to right in accordance to the positive x direction. The main assumptions made in this experiment are that air resistance and friction are negligible. The initial position of the baseball was 9.825 times 10 to the negative 4 meters. The initial velocity of the baseball was 0.22 meters per second, and the frame rate of the video was set to 30 FPS. The initial velocity of the baseball was calculated by dividing the change in displacement by the change in time for the first set of frames. Moving on to my GlowScript analysis, I created a computational model using GlowScript. In the provided code template, a ball was used to represent the baseball in the observational experiment. In the code, I left the mass of the ball as 1 because mass does not impact velocity and is canceled out when dividing the momentum update formula by mass. I set delta t to 1/30th to correspond to the video's frame rate of 30 frames per second. I altered the initial position vector to correspond to that of the observational experiment by setting the x component to 9.825 times 10 to the negative 4. I further changed the initial velocity vector to 0.22 to match that of the observational experiment. I then used the change in position kinematic equation to change the position of the ball over time. We will now compare the computational versus the tracker graph. This is an overlay of the data collected by the observational model and the computational model. The observational model is depicted in blue and the computational model is depicted in orange. These two graphs are similar, suggesting the computational model is a somewhat good estimate of the observational model. However, upon a close inspection, you will see the tracker line deviate slightly at certain time intervals, such as at 0.8 seconds. This deviation indicates the presence of an external force that opposes the direction of the travel by the baseball and prevents the object from traveling at a constant velocity. The computational model, as you saw, is very straight and orderly in nature. This indicates that there was no net force that acted on the ball as it rolled. This aligns with the kinematics equation below. If you set net force equal to 0, mass and delta t will cancel out, leaving with a perfectly linear model. One possible source of this error is the existence of non-negligible friction and air resistance. The existence of either of these two will result in a non-constant velocity and indicate the presence of a net force. Moving on to the what-if questions. How would the results be altered if the axes were changed? If the axes were changed, the conclusion for the experiment would still hold. Velocity is a vector quantity, meaning it has both magnitude, which is its speed, and direction. If instead of rolling it from left to right in the positive x direction, I rolled it from right to left in the negative x direction, it would still have the same speed, just in a different direction. Thus, if the axes were flipped or altered, the main idea and conclusion of the experiment would not change. Moving on to the what does it mean question. In the observational tracker data, a non-zero net force is experienced, as velocity changes slightly at certain points throughout the tracking. However, it is impossible to say how many forces are added together to give zero net force based on observation alone. The baseball collides with many air particles along its path that contribute to resistive forces, making it impossible to sum the total number of forces acting on the ball.